I'm sure you're all aware that we do have a telescope at the physics department. Its diameter is 0.356 meters. And because of that, I will try to use it as our standard to interpret telescopes. And perhaps one of the things we should really address is how the world's largest telescope, that's not built yet, that will be the ELT with a diameter of 39 meters, how does it compare with our Lancaster Physics Telescope, specifically in terms of light collecting power? The way to address this is relatively simple. Light collecting power will depend on d squared for each telescope, and therefore the ratio between them is just the ratio of the diameters squared. And you can very easily conclude is that the largest telescope in the world will have a light collecting power that's 12,000 times higher than the telescope we have at the physics department. This means that for every second of observations is equivalent to, even if we had our telescope in really good conditions in Chile, it is capturing 12,000 times more photons. Something else that we can already address, now focusing on resolution, is essentially the power, the distinguishing power between our telescope in physics, which we've seen is not great when compared to the largest telescopes in the world for collecting power, versus, for example, a really, really famous telescope, the almost 80-meter Lovell telescope in Manchester that I'm sure many of you have seen or at least heard of. Now let's imagine that we have a binary of stars that's 6 parsec away from the Earth, as you can see, and you'll find this in your lecture notes as well, and that this binary of stars is separated on average by something like 3.5 AU. The question we should try to address is which telescope should we actually want to use if we are to resolve the system? And perhaps you think naively, well, I'm going to go for the Lovell telescope, it's the largest. But it is important to understand that the Lovell telescope will be operating at much larger wavelengths than the physics telescope. So perhaps that sort of cancels out. As a first step, what we actually need to understand and calculate is what is the separation between this binary of stars in, say, arcsecond or radians. We're actually given a separation in AU, but also a distance to the binary system. Whenever you're given an average separation and a distance, it's relatively straightforward to calculate what should be the angle of separation between the binary stars if you sort of think back to the definition of parsec and actually invert it, like I'm trying to do right here. If you do this, you realize that the angle of separation in radian is essentially just given by the star separation divided by the distance to the stars. It is important to point out that if you just look at the ratio between the star separation and the distance to the stars in the same units, you get an angle which is given in radians. But thinking back to the definition of parsec, if you use the separation between the stars in AU and the distance to them in parsec, you automatically get the angle in arcseconds, which is shown there. This is how you would get the answer of 0.58 arcsecond. This means that stars really are separated by 0.58 arcsecond. And therefore, if we are to resolve them, our telescope needs to have a resolution that is below this. Therefore, we need a resolution below 0.58 arcsecond. We can then plug in the values, and for the Lovell telescope at Jodrell Bank Observatory, because it is a radio telescope, it operates around something like 2 gigahertz. If you convert that to a wavelength, you realize that's something like 0.15 meters. You can plug that in into the equation, and I have it in the form for arcseconds so that we can compare directly. But you realize that the resolution of the Lovell telescope, even though the telescope itself is impressive, the resolution, not so much. You can only see two sources as two sources if they're separated on the sky by almost 500 arcsecond. This means that the Lovell telescope definitely cannot resolve the system, and if you were to actually rearrange the equation to find out what is the minimum diameter that you would need for a telescope to resolve the system at those frequencies or wavelengths, you'd realize that the value would be 65 kilometers, and that's really, really hard to achieve. Fortunately, our physics telescope, operating in the visible light around 500 nanometers, even though it is way, way smaller, it actually has a theoretical, and this is important, a theoretical resolution of 0.35 arcsecond. And therefore, if we're just thinking about things theoretically, then our telescope in the physics building would actually be able to resolve this binary system. Since we know how to calculate light gathering power and also the theoretical resolution, it's probably a good idea to fix some wavelength, say in the middle of the visible, and compare some of the important telescopes, and particularly in relation to the telescope in physics that is not big, but as we've seen, it actually has a theoretical resolution that it's not that bad. Obviously, because of the way that the theoretical resolution goes in terms of the diameter of a telescope, you can very easily expect that the resolution will start to go down and be really good. And in a theoretical sense, the largest telescope in the world, that's GTC in La Palma, should get to a resolution of 0.01 arcsecond. At the same time, the relative light gathering power is actually going up much faster. It goes up as d to the power of 2, not just 1 over d on this side. And therefore, once you get to the largest telescope in the world, we're talking about something that's gathering almost 1,000 times more light than our telescope. In reality, though, telescopes rarely achieve their theoretical resolution or the diffraction limit. And that is because when you measure the resolution from an image taken through any of these telescopes, you're lucky if you get to something like 0.3 or 0.4 arcsecond, which is orders of magnitude higher than the theoretical resolution. The other thing to point out is obviously that the light gathering power by itself is not sufficient. You can have a really large telescope, but if you're actually putting the light into a detector that is incredibly inefficient, then you're not really taking advantage of the large light gathering power. And we're going to cover this in the next section, section 7.